Well, good afternoon, everyone. Welcome back, of course, to the Australian Institute of Physics Theoretical Physics Seminar Series for 2024. I'm Dave Tilbrook from the Department of Fundamental and Theoretical Physics here at ANU on behalf of the Australian Institute of Physics Theoretical Physics Group. As you're probably aware, this series of seminars has been operating for quite a few years now. And it covers a wide range of topics in theoretical physics and experimental physics, particularly experimental physics that we think might be relevant to theory or represent some new advancement in physics that physicists should be aware of. If you've missed any of those talks, you'd like to go back and watch a seminar again, they are all available to watch on the AIP YouTube channel. Just do a search under Australian Institute of Physics within the YouTube search bar, and they pop up pretty much immediately, so they're easy to find. As this might be the last opportunity I have before the end of the year, I might just remind everyone about the upcoming 47th Condensed Matter and Materials meeting, which will be held from the 4th through to the 7th of February 2025. And on this occasion, that's being hosted by the University of Queensland for a change of venue. Abstract submissions for that conference are still open, but not for long. They'll be closing in a couple of days on the 30th of November. So if you at last minute make the decision, you need to get cracking on that. The information's on the conference website. Another conference to mention just in passing is, of course, the 2024 Australian Institute of Physics Congress, which is being held at the Melbourne Exhibition and Conference Centre from the 2nd to the 5th of December. Okay, so let's do some physics. Today's talk is entitled A Description of Interactions Between Kerr Black Holes in Terms of Higher Spin Fields, and is presented by Dr. Mirian Solea. Mirian received his PhD in 1999 from the Joint Institute of Nuclear Research in Dubna, Russia, and then proceeded to gain postdoctoral experience from positions at that institution, also at the University of Padua in Italy, the University of Crete, the Technical University of Vienna, and the University of Liverpool in the United Kingdom. He also has an association with Australia and New Zealand, having held a lectureship position at the University of Canberra and a research fellowship at the University of Western Australia. And he's an honorary academic at the University of Auckland. The subject of his talk today is an approach to the construction of a field theoretical model for coalescing Kerr black holes. I think that's a reasonably good summary. Please feel free to chirp in and contradict me if I say something wrong, Miriam. As everyone would be aware, an exact model of interactions between black holes via their gravitational fields and the subsequent production of gravitational waves relies on solving the full Einstein field equations, and this is in this relatively complicated physical scenario. And this is computationally very difficult, so it's useful to have more efficient theoretical descriptions which still capture the essential physics. Now, the approach that Mirian is taking, I think, from reading the abstract, is to consider the Kerr black hole in terms of massive higher spin fields using a spin or helicity formalism for the scattering amplitudes. So I'm really looking forward to this talk. It's an area that I've been interested in for a long time. I think it's going to be extremely interesting. So once again, Mirian's talk today is entitled A Description of Interactions Between Kerr Black Holes in Terms of Higher Spin Fields. Thanks, Mirian. Over to you.
Thank you very much for this nice introduction. And yes, thank you. Let me thank, first of all, the organizers of the seminar for the opportunity to give this talk here. And yes, it will be indeed about interaction between Kerr black holes, spinning rotating black holes, and description will be in terms of effective field theory approach. And this effective field theory approach will contain massive higher spin fields. And I will give you more details about it. So it's one of the possible approaches to this very complicated problem. So basically, this is a plan of my talk. And probably you might find the structure and the content of this talk quite unusual because it contains three parts, and each of them kind of independent from the others. Basically, each of them is about a separate subject in modern theoretical physics, and seemingly they look independent, as I said, from each other, and the connection will come closer to the end of this talk, and I will show how so this all different ingredients will come together and produce the results that I would like to describe. So the first part is black holes, and I will give you a short reminder for some of might not remember about very basic stuff. What is like a Schwarzschild black hole? What is a Kerr black hole? Their main properties. I'll just flash a couple of ideas about it. Then I pass to so-called word-line description of black holes. And in particular, I just am after about one particular result, which I will be using in the part 3, which I said contains the new part, because the others two are mainly the kind of review parts. Then it will be part 2, and I'll just kind of abruptly cut here and go to the part 2, which is again seemingly independent part. Is like spinor helicity formalism for calculation of scattering amplitudes in field theory. And there's been a huge progress in this direction during the past few decades. And where all power of the spinor helicity formula has been demonstrated. And I will talk quickly about massless fields, massive fields in this approach. And then I go again, spinor helicity formalism, and go after the one particular relatively recent result, which will be again useful for what I'm going to describe, this interaction about black holes and I mean, in terms of gravitational waves. Then goes part 3. Again, starting with this brief reminder, and I'll give a general ideology of BRST approach. What and then, after I've done this general approach, I will introduce massive and massless higher spin fields. I believe that basically this part 3 will be a bit less familiar than maybe part 1 or part 2. So I'll try and I hope to spend a bit more time on the part 3. And after I introduce what this massive and massless higher spin fields, I'll go to the really new part, will be the cubic action for this rotating black hole, so putting everything together and producing this result. And so this part 3, I mean, this part 3 of part 3 is based on our paper with Evgeny Skvortsov, who is who is at the University of Mons. So here also I give some short some reviews. There are lots of reviews, excellent reviews. So of course I couldn't list them all here. And there are also books even for each of these parts. So I just chosen to give a couple of reviews for each part. So of course it's subjective, and there are many other good reviews. So this was for first part, the black holes. This is for spinor helicity formalism. And for example, the last part contains also massive spinor helicity formalism. And then the last part about higher spin fields. So I just chosen also my with Angelos Fotopoulos, because there are quite a few different approaches to this high spin field business, but this will be the one precisely that I will be using. So here's the motivation part, and my motivation part is the following. So basically, we already know that gravitational waves do exist. They have been observed experimentally. And it will be a really, it's necessary, I'll say, to have a proper field, I mean, theoretical description of this phenomenon. And direct use, because usually if we consider gravitational problem, we usually use Einstein equations. And just direct use to this problem, if you just go to full power of Einstein equations, is very complicated. Therefore, what we need to do is to do some kind of either effective field theory approach or some other approach. We will simplify and give us some help. Therefore, we use effective field theory approach, and in this effective field theory approach, this black holes will be considered as localized objects, almost like point-like objects. And this is possible because of so-called Noether theorem, which I remind you a bit later what it is. This is, of course, it's not only enough to say, we need also some approximation, or just to say that in which cases we can approximate these black holes in terms of this point-like object. And basically, we use so-called post-Minkowskian approximation here. We have weak fields, so we have this expansion in terms of Newtonian constants, but also high speed. So, but arbitrary v can be arbitrary. So basically, it looks like it's more, it's better this approach to consider scattering problem rather than the bound system. But it's also good for a bound system as well. Usually, people use so-called post-Newtonian approximation. And of course, talking about black hole as point-like particle, it makes sense when this length scale is much bigger. So it's precisely one half than the size. So basically, when we're talking about gravitational waves. So here we go, and let me start with part one. So it is the most general. So apologize if someone will find it's too generic and to reveal some parts of it. Basically, the first thing first example, what we're talking about when talking about black holes is the Schwarzschild solution, and there are not many exact analytic solutions which describe the black hole. So the first archetypical solution is Schwarzschild. Okay. So Schwarzschild solution is basically the most general solution when you have spherical symmetry and of Einstein equations, and when you have spherical symmetry and this energy momentum tensor of matter is zero. So it has this form, and this is a mass, and G is a Newton constant. So from here, we can see apparently that we have some singularity here when this R is zero. I mean, when this denominator is zero. And this expression, when it goes to zero, it basically determines a so-called Schwarzschild radius. And the event horizon is precisely at this point when we have a Schwarzschild radius. So it is a coordinate singularity, so-called, because the curvature is regular. Nothing special happens. But as we can see, for any gravitating body, we can define Schwarzschild radius. It just takes its mass and Newton constant to define it. When do we have a black hole? We have a black hole when this Schwarzschild radius sits outside the body itself. So put it a bit differently, when the Schwarzschild solution is correct all the way down to this RS. Then means that we have why it is a black hole. Well, we can play around a little bit and just figure out things about it, just for fun. For example, we say the light. I mean, when we have ds squared is zero, this is a propagation of the light ray. And if it's a radial, we basically theta puts this to equal to zero. So it is radial propagation. Then we have this expression, and we immediately see that it takes an infinite time to light onto the horizon, or come back if you like. So basically, things look like frozen when they're on the horizon. Then one more very well-known thing is that if I put just see the observer going towards the black hole, we can see that it has a time dilation because it is, I put this 3 equal to 0. dr dt and phi, and when I see that I immediately get the time dilation. That basically, that's why one of couple of things that to convince someone, let's say, at spots that maybe we're talking about such thing as black hole. So yes, so I mentioned this Noether theorem, and what does it mean in practice? That it is that any black hole in general can be characterized by its mass, its charge, if any, coordinate momentum, and angular momentum, if any. So basically, this mass is precisely the same small that I mentioned before. So for Schwarzschild, we don't have any charge or angular momentum, we have only mass. So this is the simple black hole. Then will be a Kerr black hole. And I just want to mention that I will never be using the explicit form in my talk of this Kerr metric, but it certainly deserves to be spelled out and to be shown what it is. So basically, it looks a bit like Schwarzschild, but it has the only, one main difference at the first sight is that it has an extra parameter, which is precisely angular momentum. So it is a rotating black hole. And this metric, the solution, looks like this. And it goes to Schwarzschild if I put A equal to 0. Then I'll recover Schwarzschild. But it's not just a innocuous change, because it has a dramatic consequences, and just and properties of Kerr are dramatically different from Schwarzschild one, such as like we get two horizons with place this called ergosphere when nobody can stay still outside this outer horizon. Then we have a time-like singularity, and it looks like a ring, and so on and so forth. So it's very different. But this is basically a Kerr solution. Now, this is now the question is, how can I describe this kind of word? And so this is precisely the part like one, in the sense that what I want to describe is describe this Kerr black hole like emitting or absorbing whatever this gravitational wave. And I want to model it as a point particle, and which has like mass and has spin, roughly speaking. And of course, I can do it, as I said, when this curvature is length is small. And basically, I'm basically considering this Kerr solution as a perturbation around this flat Minkowski background. So it will be like, so I basically, what I will do, I will consider a metric as a perturbation around flat Minkowski background. And this will be the Kerr metric. I will write this Kerr metric, exact one, as like eta mu nu, which is flat part. Then to be there certain perturbation, which will obey linearized field equations. So this is, I just want to say that this construction is pretty, sophisticated. So I will just give the main ideas of what the main result, without, unfortunately, being able to go into details. And I'll refer to the original paper for details and more explanations. And so then this will be their this perturbation here. And I will consider so-called Lorentz gauge condition, which sometimes called the Donder condition, which will be always possible to achieve. And on the Minkowski's background, it's known that, we have in the general relativity this diffeomorphism invariance, but here on the linearized level, it will manifest itself as this kind of gauge invariance. And it can be used to achieve this Lorentz Donder gauge. Now I'll go to the action, basically, and this total action will have, let's say, like this gravitational part, H, then it will be this interaction part, interaction with what? So I was saying that we have a body just walking through its word line. This I'll call my black hole. I have this gravitational field, which I just mentioned before, and I have this interaction between. So we'll have three terms, plus some higher order terms, which I will ignore, because I'm working in this first post-Minkowskian approximation. So it has a standard kinetic term for gravity. Then it has this interaction, and then we have something which describes, say, this gravitational black hole. So let me just simply call it black hole. And what is this size? This size is extra set of parameters which is described for me as this gravitational body. So why did I mention this previously as this so-called no-hair theorem? Because I just say that just handful parameters that can characterize my black hole. And here in particular case, keeping in mind that I want to do this Kerr solution, it will be just mass and spin. So, therefore, it's somehow on word line. It's described as this x divide. Then I introduce a stress energy tensor, and this stress energy is like called skeleton stress energy tensor, which is a zeroth order. Since it will be the differential operator with a delta function like support on this word line. So it has this form, like, and first P, and there will be higher ones, like higher pole terms in the expansion, and they will be all proportional to the derivatives, number of derivatives. So what I have is P and S, these are momentum and S. They basically as this momentum and spin. I will define the mass in terms of momentum. And there is no other variable because of this no hair. So I'm getting there just what's to get the result. So just one more thing. So then we just do the standard analysis, which standard is not simple, easier say to do than to do, but it requires analysis of this properties of the system. And well, usually it's introduced also extra constraints, which looks like this. And basically, this is a vector is called spin vector. So this is constrained why it is because it is also necessary to define the dynamics because only the momentum conservation is not enough to define the dynamic. So, so my psi, as I said, is P and A, and we also define mass with in terms of P, and U is like time-like unit vector. So now then I go to the again, it's very sketchy. I'm sorry for doing that because I have a lot of things to mention. I just giving the idea and just give a short recap after I'm done here. So basically, then I will get this interaction term. This is something that I had in the previous transparency. And I will get important thing here, also very non-trivial, that this Kerr metric, when I just did the splitting, G is equal to eta mu nu plus this H and plus something, can be this H represented in this form. And this something is a form of the gauge kind of, so basically this is a port, and then I will consider this green function solution. I get this equation from which, knowing H, I should determine T. And solving this T, I eventually get what I am get. So it will be this lowest order post-Minkowskian approximation stress energy tensor for Kerr black hole. So it contains the mass, it contains the star, which is I believe I defined it somewhere. This is the star here, and also here, and light-like vector here. So basically, this will be the result, which I'll be using in my further considerations. Now, part two. So just let me recap quickly the part one, just a couple of minutes, just because I don't want to go too quickly. So basically what I did, I just, my first part was that if first post-Minkowskian approximation, how to define the tensors of energy momentum tensor of Kerr black hole, which interacts with the gravitational wave. And this word line formalism, which I just flashed very quickly, and it was just a way, well, that's how it's been obtained and achieved. So I just had to mention just a bit the schedule, how this is going, just to get the idea and refer to the original paper for more details. So this is part two. First one has been abruptly finished. And then this is about Spener-Helisty formalism and amplitudes. So basically, we're in 4 dimensions, and we know that the light-like momentum p can be consistently represented in this form, where lambda alpha and lambda alpha dot are spinors, and they're commuting Weyl spinors. Well, alpha goes 1 to 2, and a representation of SL2 C group indices. And apparently, since the summation goes via this antisymmetric spinorial metric, so-called, p squared equals to 0. So it's also, one can see that we have this invariance, exponential I theta over 2 or exponential minus I theta over 2 because they are complex conjugate to each other. And then basically, this is a bit tricky way of saying that my little group is U1. So there's a useful relationship with you basically not spend much time on them. It's just I just wanted to show that that's what I will be using for subsequent expressions. So next, it's a vector for vector fields. We have polarization vectors, and polarization vectors will have A plus and epsilon plus and epsilon minus. I just suppressed spinorial indices here because of this notation. And this is this lambdas, which I already had. And Q is a spinor, which is called the reference spinor, which is an arbitrary one. And one can, in principle, choose this Q when I consider the scattering process arbitrary for any for each separate particle. So it's easy to see that this presence of this Q, it reflects the gauge invariance of the system. Basically, it's a 2-dimensional spinor. For example, following the argument given by Witten in his paper 2003. So it's apparent that it can have 2 terms when considering this gauge transformation, because we're in 2-dimensional space for spinors, and one term which will be just rescaling, which is trivially satisfied, and the other one will constitute to the standard gauge transformation line. So that we know from field theory. Yes, so that's precisely what I just said. And this formalism, basically, I just want to say why it is all needed, just to give one very simple example why it is so powerful. So first of all, one comment, sorry. It is so-called on-shell method, because as you can say, we're using P here, which squares to 0. So basically, the particle outside is already on shell. So the satisfy mass-shell relation. For mass, I'm talking about all masses first now, as I said. So, for example, if we're talking about 3-level amplitudes, just give you an example. So, if we have endpoint, all positively Helisty massless vector fields, and we have point scattering 3-level amplitude. So we have at most n-2 Yang-Mills vertices there, and each of them contains at most, if it's cubic, it contains 1 p, and it's quartic, it contains none. Therefore, it always be at least one contraction of this form. But choosing this reference panels equal to each other from this equation and from this properties that q squared equal to 0, we immediately see the entire amplitude is 0. So without any proof, without any calculations, this formula is exactly given the solutions that, for example, if I compute 3-level scattering for all positive gluons, this is 0. Then we can do the similar trick and say that if one guy has negative Helisty and the others are positive, or other way around, one positive, the other is negative, is also 0. And the first non-zero amplitude, it's called maximal Helisty amplitude. It has this form. And again, it was very difficult to prove it out, but using the Spinor-Helisty technique, it's use recursive BCFW relations, for example, one can easily derive this. Just this equation. This about massless, but what about massive? Because you know, we have some massive massless fields in nature, but we also have a lot of massive fields, right? So I would like to, and most part, I must say, literature of spinor-Hellyst formulas, well, I might say you often find more massless spinor-Hellyst formula, the massive one. So there is, of course, many papers of massive spinor-Hellyst formulas. So basically, what we have is a form momentum now. It's not zero, but m squared. Therefore, this matrix, if written matrix, has maximum rank. And spinors now have not only SL2C indices, but also SU2 group index. This is a manifestation of the fact, basically, that our little group is now SU2. So, a similar relation to what I had just before, and also is good for massive spinors as well. However, they have this kind of normalization, if you like, properties. And in the sequel, I will not to carry explicitly this index A. I'll just contract it with commuting auxiliary variables Z and lambda alpha will be written like this. It's just for convenience. Otherwise, notations would have been a bit cluttered. And then I also say that now, if previously I had this lambdas and lambda bars connected via complex conjugation, right? Here is all, but also have Dirac equation as well. So basically, I can convert them using Dirac equation. So from going to one basis to another, if you want. So now this massive vector field have this also polarization vectors can be written like this. And for arbitrary spin, I just was talking about vectors before now, but I can do for arbitrary spin just like multiplication of the spin one case. Now I just go to this, as I said, all the spinor-Hellyst formulas have numerous applications and for all different kind of scattering problems, loops, and not only trees, of course, but loops and high loops. And so on. But what I want to now quote is a result which I will be using for what I want to say. And these results have been obtained in 2017 paper by Arkan Ahmed, Huang, and Huang. And basically, what they did, the papers, they classified all possible 3 cubic interactions with which contain massive fields. They massive high spin fields. These are so massive fields with arbitrary spin and massless as well. And the most interesting for what I'm saying is one particular cubic amplitude, which basically has 2 spins with arbitrary mass. Basically, this is what I mean, just like. And either photon or also helicity 1 or graviton, which is helicity 2. So basically, one can see, so let us say this H will have the same 2 massive equal mass, right? So for massive momentum conservation, so because in cubic quarters we have this momentum conservation, right? We have this kind of relation. And therefore, it seems that this third lambda must be proportional to this kind of expression, and this proportional because of it's 0, right? And the proportionality coefficient is x. Why call it x? So apparently, 2 properties of this x. First, it's apparently dimensionless, and says it has if depending how I assign this weight of u1 for this L3, it's minus 1/2, then it is plus 1/2 x will have plus 1. And then just I introduce an auxiliary spiller Q, and then contract this expression with it. And so I obtain this expression for x. And then I can, in principle, nothing prevents me to not to identifying this Q with a reference spinors that, if you remember, I introduced for massless helicities. And so then X that I introduced it basically boils down to the interaction between one photon and like two scalar fields. So basically, this will be one of the main building blocks of what I'm trying to. So now I just want to hear, also this is an important point, I consider an arbitrary 3-point amplitude, and I just want to see the structure, what kind of structure I can get in terms of. So as I said, it's a two-dimensional space, and I can choose a variable in terms which I will expand it. And since I am to assign the proper weight and so on, now, this will be, I will choose to expand it in terms of this lambda 3 and epsilon alpha beta. This is epsilon alpha beta is a spinorial matrix that I introduced before. So this will be this arbitrary. So this is basically a kinematic argument, and it's expanding this arbitrary like 3-point for two spin field, highest spin and mass and helicity h, which I kind of keep in mind is either 1 or 2, but argument goes for an arbitrary one. It will have this form as this is coupling constant. So let me give a command. So in principle, what's going on? I have not referred to any Lagrangian yet. That's what I hope to do at the end of the talk. So if I take one operator in the Lagrangian, it can produce heaps of different terms in this expansion. And we don't know what will be. You just need to take a particular term, work on it, expand, and get what kind of expansion we'll get. This is polar. What kind of structure can we get at all? And this is what is possible. And then if I introduce massive spinors and play around with these notations that I had before, I get this kind of expansion. And what's is one of the main points that I want to emphasize. Let us conjecture that all constants except G0 are 0. So can we just get such a field theory which produce only the first term? So then that means that this 3-point amplitude between S, S, and H will be very simple, just one term. And this is called, in the paper of Arkaneham and Huang, is called minimal coupling. So we all know that, there is this kind of usual notion of minimal coupling, and is it connected? Yes, it is. Also, the point is that, for example, I can give you an argument. So when we have interaction of two massive, let's say, spin one fields with two massless spin one field. So it's a very well-known physical example of, let's say, like Higgs model or something like this. So we know that, the coupling, in order to avoid the problems with unitarity, will have only very specific form, which is obtained by a spontaneous breaking of the symmetry. Because it is, I'm referring to the very well-known fact that usually quantum theory of massive fields is not unitary unless they obtain mass via spontaneous breaking of symmetry. And so this is what it's about. So the original argument of choosing maybe what happens if I kept this term only, it will be if I want to have good ultraviolet behavior. So basically, that's what I mean. And I end up with only two. And since I'm interested not, so just to reiterate, my massive field, high spin fields have mass, m, and they're equal. So, and arbitrary spin. However, there are massless fields, are lower spin fields, so-called. It's spin 1 or spin 2, which is graviton or Maxwell. And then I just go back to what I obtained before. That's why I needed So I just Fourier transform this T mu that I got. I'm back at the curve now. And now what I will do, there is a way, if I consider this interaction, this is a trick, and if I have time, which I a bit doubt, but I have one slide just in case, I can explain that taking the classical limit of this amplitudes, is this one in particular, this will be a bit different, will reproduce precisely the interaction of this three vertex which I obtained from the word line formula, which is classical limit. I mean this. I mean big low momentum for k and high value of spin. And this is a very key point as a magic, if you like, to the things that we have on one side. We firmly obtained, and this result has been already firmly established. There are many check, and the people go further than cubic also, that on one side we get this cubic interaction. When I say cubic interaction, apparently I mean this, for example, you have a black hole, it emits like gravitational wave and it carries on. So basically you can consider the spin, two spin m, and on the other side, I have this high spin, which in classical limit gives precisely the mapping between these two. And the question, and what I am now after, because all these were on-shell arguments, can I rebuild an action which reproduce this picture? So can I, or put it a bit differently and boil it down, can I write an action for this two massive high spin fields with the same mass, and one is a spin 1 or spin 2, and gives this Arcani-Ham and Huang paper in vertex, like on shell. So now this is part 3. Let me so I should probably speed up tiny bit, but well, I'll try. So let me recall you what is a BRST approach at all. So first of all, if I have a system, a mechanical system, which is a gauge invariant, that means it contains some first-class constraints. Because first-class constraint is a synonym. Basically, first-class constraints, constraint is that, for example, if I do Hamiltonian analysis, if any function of canonical momentum and coordinates gives me 0, it's called constraint. It's called a constraint. So basically, I also have Poisson brackets, of course, in classical mechanics. If I do between Poisson brackets between these guys, I will get an algebra. This is the definition of first class. Now, how can I quantize it? The quantizer follows. So I just go from let's say canonical quantization, not passive. I just go from Poisson to commutators. That's what I have in commutators. Let's say for simplicity, it has a Lie algebra structure. So this user constant. For each G, I introduce the anti-commuting coordinates C and B, and they are anti-commuting if this were so they have opposite parity Z2. And then this is an idea of the BFD theorem, Batalin-Fradkin with Kulisky theorem. So basically, so this gauge invariant, also this has a gauge invariance, we can introduce so-called BRST charge. And this BRST charge has the following form, which is written here. So it basically comes from the fact that most general Hamiltonian is this canonical one plus a commutator of psi with some arbitrary function. And this arbitrary function is basically contains all gauge freedom, whereas Q doesn't care about the gauge. And fixing this extra function is the same as fixing the gauge. And since all Hamiltonians are physically equivalent, physical state is singled out by requirements that Q physical is 0. This is basically BFD. But also, since the normal physical state should be good, positive, not 0, that means that I cannot write as Q is equal to lambda. Mathematically saying that we are after cohomologies of this BRST chart. Let me give you an example of this very simple, just what I'm talking. We all know, for example, word line like action for massive spinless particle. So it has this form, right? When this is it's word line parameterized by time tau, and this dot means dx by dt. So if we define the canonical momentum, which is a derivative of x dot, then I will get this expression. Okay. Sorry, just one question. Can you hear me, just in case?
Yep, it's perfectly good.
Okay,
Sorry.
thanks.
It just took me a while to press on the button.
Okay, cool.
Carry on.
Yeah, thank you. So basically, P mu is like this. And if I square it up, I will find that P squared plus M squared is 0. That means what I meant to constraint. A function of P, not Q here, but not P, is 0. Then, looking at this guy, there is, of course, commutes itself. So the U is simple 0, is then only C, which is non-zero. I just write the simple BRST charge as simple as. And since I said that C is anti-commuting as rest anti-commutator 0, that means that C and B squared, any, is 0. Then important. So just to remind, this is mathematical notion of Grassmann variable, right? So it doesn't have any analogy of usual C numbers. It's mathematical symbol, which has very important application in math. And so this is, when I say C0, it doesn't mean that C itself is 0. And especially if it's anti-commuting, it means basically that it's a non-trivial statement. Because any bosonic operator anti-commutes with itself, but it's not true for fermionic. Any fermionic does not anti-commute with itself in general. Therefore, the fact that this Q squared is 0 is non-trivial. Therefore, the physical state condition is C is equal to P squared plus M squared equal to 0. And of course, since C is not 0, as I said, C is 0, the solution is P squared plus M squared equals 0. This is, as we remember also from field theory, is like a Dirac quantization. We have constraint when positive on the physical field. Now let me ask myself a question. And can I at all build the field theory which gives me this equation as an equation of motion? And to do it, I do the following. I recall that dc is 0 or c0 is 1. It's like a Grassmann integration rule, which is the same as differentiation. My physical state, I will write it. Phi x is 0. On some vacuum is equal 0. And I write all the possible Lagrangian, which I can invent with this stuff. This is physical and Q sandwich in between. I introduce, put it here, and I get usual Klein-Gordon Lagrangian. So basically, what I was talking about. So I had some kind of expression. I want my field to obey this condition: P squared plus M squared is 0. And can I at all build field Lagrangian, which gives me this equation of motion? The answer is yes. I use this BRST technique. I just introduce auxiliary ghost variables, write BRST chart for it, and put it in the Lagrangian of this form. Integrate this ghost out, and I get what I want. Now I want to do the same thing for so-called high spin field. So in the remaining probably 10 or a bit 10 something minutes, I will try to squeeze it out. So basically, one of those terminology, usually when people talk about high spin fields, they usually mean a massless high spin field. But it's not exclusively so. And one example about high spin fields, which we know, and massive high spin fields, which is perfectly consistent, is string theory. It's basically a theory of massive high spin fields. Because precisely the high spin fields are responsible for ultraviolet fineness, and all this, because they do it, the job under the hood. They often, we don't spell them. I mean, we use other technique, but that's what is going on. So basically, they can often consider an anti-de Sitter space, or flat background. So basically, what I want to do, I want mass shell, which is box minus m squared is 0. Then I want transfers, because since my metric is sign definite, that means that ghost should be present and should be traceless as well. But traceless can be, cannot be, depends what I want to describe, because this is a so-called irreducible representation. And I will find, and we will find more convenient to drop this constraint. Because if these two are not satisfied, that means that something is wrong. My theory is kind of sick. But if this is present or absent, it doesn't really matter. It's just question what I'm describing. That's it. So it will. I will try to show that it's easier to drop this one for what I wanted to do. And then I proceed. Just keep in mind this example of this massive particle that I was talking about. Right? The only thing that in order to consider high spin fields, which I said that they are tensor of high rank, it's easier to introduce auxiliary oscillators. You see, if talking about free system, it might be a matter of taste if you want to describe them or not, introduce this alphas or not. But I personally have not seen any paper on interacting vertices without use of these auxiliary variables. That's why I kind of feel necessary to introduce them. Then, in this auxiliary Fock space, I will introduce this mass shell, which is p squared plus m squared. And these guys are kind of transversality conditions. This part is the transversality. This is correction with mass. And from this notation alpha d, you can say that I kind of can start from massless fields in d plus 1 dimension and dimensionally reduced. So it kind of looks like you can, if you like, and P, M, and M will be this extra moment compact. Then now I have 3 operators. Therefore, I need 3 pairs of them, of this anti-commuting variable. And then I will take this physical, what I called, but now I expand not only in terms of this alpha oscillators and alpha Dagger, alpha mu, but also in terms of this ghost oscillators, this anti-commuting one. And then since they're nilpotent, I never can have c squared or b squared equal to 0. I have very limited form of the expansion. There is also thing that's called ghost number, which helps to prove that this is the only sensible expansion that we have. And each of them, as I say, are expanded in terms of only alpha and alpha d oscillators, and this alpha s and this s is basically the power, total power of oscillators. So why it is so, just a hint, because if looking at the BRST chart, which I will write later, everything commutes with the total number of oscillators minus this. Therefore, you can see this is s minus 2, but we have also c and b, makes it s total. And this is s minus 1, but here 1b, and so makes s total. And as I say, each of them are expanded in this form. Now, what's just going a bit ahead? These two are not physical fields, and alpha d dependence is also not physical field. So I will end up with only physical part, which is massive and transverse. So basically, we have a non-zero commutator. I just simply count the algebra between these 3, and write the BRST chart by the standard recipes that I had before. Then will be this quadratic action. Everything, just keep in mind this massive particle example, basically. That's it. And of course, this q squared is 0. It is invariant under this transformation, where b, again, counting these oscillator numbers, is just lambda is of this form. Example, again, massive spin 1 field. So applying this, what I had before, it will be just these 2 terms. Lambda is just this. And this d, because remember what I had before, s minus 2, and s minus 1. If s is equal to 1, it will be 1 here, it will be nothing here, and it will be 0 here. So here you go. This is just term with only 1 oscillator, either this or that. C0 has none. And lambda, as I said, the same argument has also no oscillator. Then what I do, I just take these guys, take the BRST charges, always the same, put it here. Then I integrate the C0 and normal order in terms of C and B, the rest, which is the C plus B minus and so on. And I end up with this kind of Lagrangian. Then what you can see, you can use this equation of motion of C, it's algebraical because it has no derivative, and remove it in terms of its own equation of motion, put back in the Lagrangian. And that's what I will get. So basically, it's a Stuckelberg. Now I'm gauging away, and then I will get only massive. So unfortunately, I have probably to skip a few things, but let me just show that I can repeat this strategy for arbitrary S, and so must be S minus 1 here, sorry, my typo. And repeat the same and gets pretty simple Lagrangian. If I will be considering traceless fields, then I would have had more complicated ones. Therefore, the kinetic part is much simpler looking at it. How do I do the interactions? I need to modify my linear transformations because I want to have some sort of nonlinear gauge transformation. Otherwise, it will be impossible to get non-trivial interactions. So I basically deform both gauge transformations, and I introduce 3 copies of the oscillators. And that's how it is done. And then I write a cubic interaction of this form. Also, I have 3 copies of oscillators, 1, 0, and so on. And then the invariance of 0 orders I do have, it is q squared is equal to 0. And the first order, which is V3 cubic vertex, must be BRST invariant. These are conditions of allowed cubic interactions between these arbitrary spin fields. Finally, we can do the solutions. And solutions have been found in the paper by Mitsayev in 2012, when we just basically have BRST invariant quantities, and each of them is BRST invariant. So basically what I mean is that since each of them is a BRST invariant, any function of them will be the BRST invariant. Therefore, any function of these guys will be allowed legal BRST cubic vertex. Now, my last point, and I will have here. So now I want from this setup recover precisely the result of Arkani-Hammett-Huang. And then I can start doing simple examples and putting allowed combinations and see how I can get the result. So for example, if 2 scalars, complex scalar and let's say 1 vector, I have only this K3, the first power. Put it here, and I exactly recover the result here when I rewrite the result in the spin-Orgellisti formalism and going on shell. Similar, I can do 1, 1, 1, 1, 1, 2, all those simple examples. The most non-trivial will be 3, 3, 2. So 3 again, first 2 are massive, third is massless, and it's gravitational. So we'll again say what kind of allowed combinations of this equation forms I can get to obtain the result. And I say that I can have these forms, but also on very, very specific fine-tuned coefficients between them. And this one will give me the minimal coupling. You can see that this is a mass term, but also the different power of, this has a force power of P, derivative, force derivative here and here too. And basically, this generating functional we can do and was obtained by in this paper. But what we can do is writing this BRST invariant forms, which you can just do this off-shell completions. And what I mean, just let me maybe stress a bit more here, because all this BRST formalism is completely off-shell. It gives us the Lagrangian. So basically, when I wrote it here, this is cubic Lagrangian. And therefore, and these extra fields, as I tried to give the example in terms of the C here, it's just necessary to maintain gauge invariance. You just gauge it away, and then you get only physical field. So basically, with these forms, we just put and write this vertex And this is SS1. It's called the root care because this is when two massive high spin are interacting with one massive massless vector. It is useful because for a very well-known factor, usually gravity, roughly speaking, is square of Yang-Mills, right? So basically, we can consider interaction of vector field, and then from this we can infer quite a few things about gravitational interactions, which are more complicated. So I tried not to go over time too much. I think it's 9:12, and now I basically go to the conclusions. Sorry if I was last bit was a bit too fast. If I have time, that just remaining maybe a couple of minutes, I'll just go quickly through the last part because I feel I might I was a bit too fast here, and I can.
That's fine. That's good.
Yeah, just 2 minutes, and yeah. So basically. About this high spin fields, the main points. So they are described by arbitrary S. They are massive in general. Here. Well, just if you say here, and they must satisfy mass shell and transversality conditions. So they, by the way, massless fields have numerous no-go results about the interaction, but none of them applies to massive. And I say one of the example of massive high spin fields was string theory, for example, with a very specific dependence of mass of spin, but not going there now. So therefore, how I used this, I just kept in mind this particle action, massive spinless particle. I know what kind of equation should they obey, and use so-called BRST technique to reproduce a field theoretic Lagrangian for it. Free Lagrangian, right? Because I'm talking about free system. Similar here, these are free equations, linear equations. Therefore, my Lagrangian will be quadratic first. And so I just introduce this transversality mass shell and this gradient one, which I need. Right? It brings about this extra fields, auxiliary fields. Quite common thing when we're talking about gauge invariance, gauge artifacts, if you like. Write the general expression and put it back in the BRC invariant Lagrangian, write this charge, everything, and this is my Lagrangian. Looks funny. Okay, I just remove all oscillators, bosonic, fermionic, everything, and I get normal Lagrangian for massive speed field. And I can prove that all of them, the C, D fields, can be gauged away. And phi, this main fields, this alpha D is also gauged away, and so I end up with only physical fields, which is massive and transverse. It can be just strictly proven on the free level. Example of here, it was like Stuckelberg formulation of the massive field. So I have the C, which can be removed by its equation of motion. It can be done for arbitrary spin tricks, because this C doesn't have any kinetic term. And this guy is like a standard Stuckelberg field. I can gauge it away with a shift, end up with massive fields. This is gauge invariant formulation for massive spin one field, and I can do it for arbitrary S. This is a Lagrangian for arbitrary S. I did not remove this alpha oscillators because they are still there, otherwise it would have been a bit bigger. This is a compact one. And that I mean that I can gauge completely gauge fix, and I left with this kind of field only. That's it. So massive and transverse, that was exactly what I was after. Then what about interaction? Take 3 copies of this alpha oscillator. Take 3 Fock space, 3 Fock spaces. And what we need to do? Deform the gauge transformations, because otherwise we'll never get non-trivial interactions. Deform the Lagrangian, and this is the same cubic vertex sitting here and here. The only thing that it will be different parts will taking part in here and taking part here, but BRST languages are the same. The one part of it will contribute here, the other here. And free one is invariant because of the BRST Lagrangian is invariant, as I showed before. And in order to V3 will be a correct vertex, it should be BRST invariant, Q1 plus Q2 plus Q3 on V equal to 0. One can solve it. The solution will be done here in this paper. All this thing, I mean, for arbitrary classification. And I take this when 2 masses are 0, and these are precisely BRST4. Each of them is BRST invariant. Therefore, any function of its BRST environment. The next is just to take the correct combination of them and to reproduce the paper, I mean the result of Arkani, Hamed, Huang, and Huang, which in turn, as I showed, is precisely kind of gives interaction of curved black holes with gravitational wave in the classical limit. Therefore, I can say that doing all this thing, I get pretty much the field theoretic description of this interaction of curves. And I can, this is the result that I showed. This is a cubic vertex. And basically, that's it. I already said a kind of conclusion as well. Sorry for going a bit over time.
No, it's fine.
I did not take too much time from you, so thank you.
Thanks very much, Miriam. That was a very interesting talk. I was going to ask you about BRST invariance, but then you covered that in the last couple of slides. I don't see any questions in the Q&A panel, so maybe I could ask a couple of questions I took notes about as you were going. So you're making, I guess things don't get much more complicated if you relax the assumption that the two black holes don't have the same mass.
Well, this basically it's it might be a bit because basically it's one two black hole. I just can imagine one black hole going and emitting, so apparently it's mass the same.
Yeah.
Of course, there must be some mass changing interactions and so on. It's I think that's what precisely means. It's very interesting, but then we need a good mapping with field theory. And all many nice properties that I described, it was this Arkani Huang paper when the masses are the same. It might be possible, but it might get a bit more complicated, but probably not undoable. So, but I don't think that people done it, as far as I know. So,
no, okay.
But it's of course very interesting question. Apparently, also I might say there is one more thing. I kind of mentioned it, touched upon it a bit. You know, I describing reducible representations. That means that it's just each of these Fs, it contains lower spins as well, even on the free level. You say, there is nowhere the traceless condition. So basically I have S minus 2, S minus, and this is also open question, which I found we mentioned, but it can hopefully describe spin changing interactions between black hole, which is a very interesting question. Yeah.
No, that's interesting.
But the main point, original motivation of looking at reducible ones, not trace, because BRST charge itself in the Lagrangian is much more difficult for irreducible modes, so-called front-down modes. Okay. It's really complicated. Even one can handle it from the. There have been papers recently how to do cubic interactions for this kind of field, but you know.
Okay. Sergey Kozenko would like to ask a question, so I'll just make sure that you can speak. Sergey, can you? Are you? Yeah, I think you can talk. Yes.
Okay. I actually have several questions. Maybe just the one I just typed, but. In super-ion Mill theories, maximally helicity violating amplitudes vanish. I mean, this is old result. Can you see that in the formalism you are using?
Yes, it's possible. Yeah, so people did MHV also for super-ion mills. Well, I don't need it here, but well, I mean, I wasn't using here, but you know, it's possible.
Second question: what will change when you replace Minkowski background with, say, anti-de Sitter?
This is also a very good question, and I might think how one can reformulate. Well, important thing is, of course, to find first this T, energy momentum tensor in this case. This is what I was trying to do the first paper by Guinness and And second, yes, it will be very good to see what kind of 3-point amplitude. This is a very interesting question, really is. I mean, then it will be something about maybe like ADS-CFT correspondence there, and people already developed. I mean, there were quite big progress about spinor helicities also on IDS, and then it will be like a question of cubic interactions on ADS. This classification of Berenstein invariance vertices, it's an old standing problem. I mean, already going back to this form of Messiah. This is what I have just in front of me. Again, I remember, well, just say we had very long ago, we tried to do this solution in our old paper with Angelos Fotopoulos, Josip Burbiner, Anastasios Petko, just to write a similar classification on ADS. Also, I must say it was 2006. So before full classification in IDS here. There was a written Messiah's paper was on LightCon just before. Well, why is a long story? Because it's also a good question how to write these formulas on ADS. And probably it is a way, and there are some ideas, but I would really love to see it written somehow. It's not undoable, but you know, then it will be like. So in our paper, what I mentioned, we just set up general formulas, general equations, but I haven't seen them being solved generally. It's mainly the zeroth order is a cosmological constant. Oh, IDS radius is the same as here. But then will be correction, and I haven't seen them written in analytic form. Usually people say, okay, it exists. I think that there is a statement that, as far as I know, that each cubic vertex on flat has its deformation on ADS. So it's possible. But to written in a compact and nice form, I would really love to see it. So I mean, it's a really cool question. It would be really, really interesting to do.
Yeah, certainly. Yeah. While you were talking, I was trying to see how much of the physics would be captured by this model in terms of the interaction between the two black holes.
I think that, well, yeah, if it applied, because you see, let me give an example. All the spinor helistic formalism is a huge application to scattering processes that people are doing, like, you know, real physics, if you see what I mean. The same. So if
no, this is real physics. Don't worry.
Yeah. So this is basically what I try to say is the formalism, the how. But yes, using developing field theoretic approach, we basically will have mapping. So do field theoretic computation, the mapping through the gravitational interactions. Yeah, it's precisely
the restriction to the cubic action, though. Does that imply any restrictions on the applicability? I mean, for example, if I have a pair of inspirating black holes, the very last part of the coalescence where we have very strong fields, and perhaps we have strong back reactions in terms of the interaction between the black hole masses and energy transfer with the gravitational waves that they're producing, those sorts of higher order effects, are they likely to be captured in this?
Oh yeah, sure, and that's precisely, I might say, it's work in progress, basically. So you see, in terms of off-shell methods, people already done this kind of computations. I'm talking about Lagrangian, and this is more complicated because, yeah, sure, because what I'm talking about cubic, because it's like first is a cubic, right? Then go to the higher, because it's like a first block. So no, it's not just it's restricted and cannot do anything else. No. It's just basically the first, because if you don't have this and you don't have free part and you have cubic, you have nothing, right? Yeah. So it's a necessary first step, but of course it's not the end of the story.
Yeah.
Most interesting is, of course, but it's already, I found it pretty fascinating when you have this completely different approaches. and they can be connected in this way. Then I say, okay, let me do some computation in field theory.
Yeah, no, it is very interesting. Yeah, it's a very.
So that's precisely what it's about. So of course it's basically just cubic, but then yes, higher one, sure.
Yeah, okay. Well, that's great. I don't see any other questions. So let me thank you once again, Miriam. That was a very interesting talk. And I just remind everyone, there was a lot of material here, which was all good stuff. If you want to go through it more slowly, of course, it'll be up on the YouTube, the AIP YouTube channel within a few days. So you
And
go
I
through
can
it.
also send your my slides. So,
Oh, marvelous. Okay. All right.
so if because some people prefer to read it.
Yes, absolutely.
I will after the talk I will forward.
Oh, well, thank you. All right. Well, thank you very much. Thank you very much, everyone, for attending. We'll keep everyone informed as to what's happening with the series over the next few days and weeks. Thank you all once again, and thank you, Miriam, and bye for now.
Thank you. Bye.
Thank you.